As general theory of relativity predominantly speaks about the geometry of space-time, hence a thorough, deep and clear understanding about the mathematics of geometry becomes increasingly important. In the last episode, we learnt about differential geometry, an important tool to learn in our journey to understand general relativity. However, a much bigger and broader picture of geometry plays an important role in relativity: non Euclidean geometry. Yes, in this video we are going to look into this part of the geometry which pertains to a much comprehensive and all-embracing aspect of the physics of general relativity. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the 5th episode on how to learn mathematics for general relativity. Before we go ahead, as usual, here is a quick recap, but don't worry, I have given this entire video, the previous 4 videos, in the playlist, as well as it is there in the I button, which you can very well go ahead and check it. Now, in the last video, we talked about differential geometry. So we started basically what is the difference between flat space-time and a curved space-time. We looked a lot into what are called manifolds and why manifolds play an important role in understanding general theory of relativity. We also learned that geometry plays an important role in defining gravity, because gravity in general relativity is no more a force but a manifestation of the curvature of space-time. So general relativity presents a completely different picture, and we learnt about that. Also, we learned that with this trampoline analogy, the geometry of space-time tells objects how to move, and the presence of mass and energy tells space-time how and in which direction to curve. We also try to understand this question, that how to define this geometry, how to give a mathematical framework and show the relationship between curvature and distribution of mass and energy. And for that we know that we knew a new mathematical tool which is called differential geometry, which we covered in the last video. We also learned that what actually is the word differential and geometry means. It means using the rules of calculus or using calculus on the geometry. So these two words, differential and geometry, comes together. We also learned that the differential geometry is something which is very local in nature, and that is why gravity is caused due to the local curvature, and in order to measure that we need calculus and we need to study the structure of space-time. We also saw that the positive, negative and the zero curvature can be calculated using different rules of calculus. So using differential geometry to study is used to study the behavior of the local surfaces, and the new mathematical tool differential geometry actually helps that in our learning. Then we looked into what are called manifolds, and manifolds are nothing but actually a special kind of a structure which, when magnified or zoomed, comes into what is called a locally Euclidean space. So if you study one particular manifold which is quite similar, or what we technically call homeomorphic, then the physics around that part will be similar to that of the next part. We also learned about homeomorphism, smooth functions, which I'm not going now because it is a quick recap. And we also learned about the 2 books which are very important, John Emley's Introduction to Smooth Manifold and Loring W. Tu's An Introduction to Smooth Manifolds. Apart from that, we saw a lot of online, I would say, lectures, YouTube videos, blogs, etc., which gave a complete kind of an understanding, those who are willing to learn online, about the concepts of manifolds. Finally, what we saw is that we saw a large number of books. I actually gave a complete review of those books also, which book to read, which book not to read, the Spivak's books, the elementary differential geometry, and what are the reviews, what are the content, what are the things that are being covered in those books. So this was where we ended our last video. You can go ahead and look into part 4 of that video, where there is a complete understanding of differential geometry, its relation to general relativity, and how and where to go and what are the books to pick up and learn. Now we come to this part of our video where we need to understand that what is non-Euclidean geometry. Don't worry, I'm not going to go details into the non-Euclidean geometry, but a basic understanding will be very important. Now, as you understand that non-Euclidean geometry is a type of a geometry which arises when Euclid's 5th postulate, that is the parallel postulate, is replaced with an alternative. So as you can see that Euclidean geometry is built on a set of basic truths which are called axioms, and non-Euclidean geometry is actually obtained by tweaking these axioms, specifically Euclid's parallel postulate. These tweaks leads to alternative geometric realities. Now, there are two main types of non-Euclidean geometry. The first one is called the elliptic geometry. In this geometry, through a point not on a given line, there are no lines that do not intersect the given line. I mean to say the sum of the angles of a triangle is always greater than 180 degrees, and that is why the curvature is positive. The next one is called hyperbolic geometry, and in this type of a geometry, through a given point, not on a line, there are infinitely many lines that do not intersect the given line, and this type of a geometry has got something which is called a negative curvature. So these are the two broad categories, the elliptic and the hyperbolic, and these has very deep relation in terms of understanding the mathematics and the physics of I would say general relativity, and we were going to look into that into the next part of the video. So in non-Euclidean geometry, as you see, the basic concept is that of a curvature. So how do we measure the curvature, etc.? That is what non-Euclidean geometry deals with, and it describes how space bends, and it actually differs from Euclidean space. So as you can see right on this illustration, that this is an elliptical geometry and it has got a positive curvature. That means the sum of the angles of the triangle is more than 180 degrees. Although elliptical geometry, the ellipse actually looks like this, but you can make an analogy why this is positive curvature. The next one is called the hyperbolic geometry, and you can see that the parallel lines here are converging. In the hyperbolic geometry, the parallel lines are diverging, and that is why it has got a negative curvature, and the sum of the angles of a triangle is less than 180 degree. And that is why this is how actually they look like, the branches and the asymptotes. Now, as you understand, these are not actually related to the typical Euclidean geometry. It is a complete transit from that. So as you see that the shortest path between 2 points in curved space-time. So in Euclidean geometry, geodesics are straight lines, while in non-Euclidean geometries, I mean to say they can be, geodesics are straight lines, but these can be curved. So here is a kind of an illustration. You can understand the behavior of parallel lines would differ in terms of Euclidean geometry, because in hyperbolic geometry, as you saw, the parallel lines diverge, while in elliptic geometry the lines converge. So let me have a look onto this. Yeah. So here you see they converge, and here they are diverging. So same thing happens over here also. So these are converging, and in hyperbolic geometry the parallel lines are diverging. Also another thing which is important is that the sum of the angles of a triangle, as you can see in the first figure, is less than 180 degrees, and the second one is more than 180 degrees, and that is how actually the things change. Now this is a very broad and a basic definition of non-Euclidean geometry, although there are many more things which you can actually learn through, but this is just to let you know or set the stage of what is non-Euclidean geometry. Now the question that you might have in your mind is that why do you need non-Euclidean geometry? I mean to say, if you're learning the general relativity, there should be some kind of a resemblance between learning and applying that to the knowledge of general theory of relativity. So in this part of the video, we will learn about why do you need non-Euclidean geometry. Otherwise, I mean to say, it would just be learning without any basic objective and motto. Now, as you can see, the light cone in special theory of relativity is something which is a kind of a hyperbolic geometry, a hyperbola. So as it was designed by Einstein's professor Hermann Minkowski, so the purpose was to create basically an invariant space-time, and to uphold the causality purpose, Minkowski designed a kind of a non-Euclidean geometry. Now this is actually taken from the Internet Archive, and this is actually the handwritten diagram, although it was in black and white. Later it was colorized. This is Minkowski's original drawing of the light cone. And from this drawing, you can very well understand that the hyperboloid model, which is also known as the Minkowski model, is a model of n-dimensional hyperbolic geometry. Hyperbolic space is actually embedded isometrically in the Minkowski space, so that the hyperbolic distance function is inherited from the Minkowski space, which is somewhat, you can say, similar to that of a spherical distance inherited from in Euclidean distance. And there are many instances about hyperbola and this model which has been used in Minkowski in his light cone revelation. Now you can see there are several research papers also. For example, these two research papers actually speaks about Minkowski spacetime and hyperbolic geometry, geometry of Minkowski spacetime in terms of interpreting at hyperbolic angles. These are very good research papers taken from arxiv.org. You can go ahead and read it. So finally, what we come to know from here is that the light cone surface can be described by a hyperboloid, and this is due to the nature of spacetime in special relativity, and for that you need to learn hyperbolic geometry. Also, the cross sections of the light cone, which I have not shown here, if I take the time slices, they form hyperbolas, which indicates a very close relationship with hyperbolic geometry. So that sets the stage and gives you a reason and a motto and an objective that why you should learn hyperbolic geometry. The next question comes is that elliptic geometry, does that have any resemblance in terms of understanding general relativity? So the answer is that in an idealized cosmological model, the universe has a finite volume, and it is something similar to that of a sphere. And you can imagine, because elliptic geometry has a positive curvature, the Friedmann-Lemaitre-Robertson-Walker metric, FLRW metric, can be considered, which can be a spherical or elliptic spatial geometry. So in general relativity, typically I would say ideal conditions with a uniform distribution of mass, energy, position, momentum, everything, you can get a positive curvature. And this positive curvature obviously means that it can be modeled using elliptic geometry, and here space-time would be finite and it would curve back on itself in a closed loop, much like the surface of a sphere. So I mean to say, these are ways in which you can understand and model a closed model, a typically positive curvature using elliptic geometry. So from here we can draw the conclusion that elliptic geometry is related to general relativity, but it is on ideal conditions because it helps to describe the properties of behavior of such universe. But in reality, this is not an isometric universe that would have a positive curvature. So it is used much more on a broader framework. As I have written, Riemannian geometry, elliptical geometry do provide useful and special cases for understanding cosmological models. So the two aspects of non-Euclidean geometry, now that we have seen the hyperbolic geometry, the light cone and elliptic geometry for positive curvature, there are several other reasons that you should know non-Euclidean geometry coming up into the next part of the video. The first reason is the historical understanding. Now you might be ignoring this, but you will understand eventually that the evolution of non-Euclidean geometry serves as an important tool, because without knowing the history you won't be able to understand how the modern physics, and most importantly why the modern physics require non-Euclidean geometry. So the key figures like Gauss, Bolyai, Lobachevsky and Bernhard Riemann, you need to learn them, you need to learn the evolution, and then the learning of physics and most importantly general relativity becomes much more interesting. Also, the development of non-Euclidean geometry actually led to the foundation of the more complex geometries essentially dealt with general relativity, manifolds, etc., which you can learn very well. And if you learn the historical perspective, then it comes as I would say, a great mathematical tool used in general relativity. For example, how tensor calculus and differential geometry evolved. So remember, differential geometry is one of the tool, but the overall super picture is that of a non-Euclidean geometry. Also, we can say that nuances of non-Euclidean geometry, how to understand the curvatures, etc., the concepts are much more clear, and it essentially gives you a mathematical rigor in tackling problems with general relativity. This is the final, I would say, summary, that if you understand the non-Euclidean geometry, then it provides the necessary mathematical framework, historical context, mathematical rigors, everything enhancing your concept and your clarity and your mathematical proficiency. This actually deepens your understanding in understanding the universe structure, and thereby going much more deeper into the nature of gravity, which is the core pivotal force of general theory of relativity. Coming back to the next part, the big question is that how do we understand all those non-Euclidean geometry, taking into consideration the history, the mathematical rigor, all those concepts. For that we will now come to the most important, that is, what are the best books of non-Euclidean geometry. The first book itself that I am going to show you is called Euclidean and Non Euclidean Geometries. Now hold on, why I am talking of this book, Euclidean and Non Euclidean Geometries? Because it will give you again a brush up of the Euclidean concepts, and built on this will be the Non Euclidean Geometries. Let me talk about the edition and show you the photographs, because this would be the first edition, second, third and the fourth edition. This is a famous book I have also cited in my earlier videos, Euclidean and Non Euclidean Geometries by Marvin J. Greenberg. Now you can pick any one of those, doesn't really matter about the edition, but this is how it looks. If it is a 665 pages book, so quite a thick one, because it comprises of both Euclidean and Non Euclidean geometries. Yes, the price on the Amazon part would be a little bit higher if you're going for the hard copy, but even the soft copy, the paperback, as you can see, it's quite high in 16,625 INR, so it is quite high on the Amazon India side. If I go to the Amazon.com, you will find it is almost coming to $34 to $13 if I take the paperback edition. So hardcover would cost around $189, $190. So you can very well purchase it from the dollar price if you want the paperback cover. I mean to say the earlier edition. So we come back to the book. Now if I go into the Amazon review, okay, it is 66%, and this is the person, Marvin J. Greenberg, a very famous author from 1959 from Princeton University, and he received his doctorate under the famous Professor Serge Lang. Now these are some of the reviews which you can check, whether for class or for personal tutoring. Remarkable, and then 4 stars, it was a good deal, excellent as described. So overall you can say that it is a very good book to read. Now this book, as it covers both Euclidean and non-Euclidean, that means it should start basically with the Euclidean part and then it goes into the non-Euclidean part. So it gives you a very good thorough understanding. But most important is that who should read this book? As I told you that it is important for every book and for every readers that should understand that who should read this book. Professor Greenberg gives a very good clarity. Now you see here, prospective high school and college geometry teachers are presented with a rigorous treatment of the foundations of Euclidean geometry and an introduction to hyperbolic geometry. General education and liberal arts students are introduced to the historical and philosophical implications of the discovery of non-Euclidean geometry. That means you can be a high school, a college geometry teacher, or you can be even into general education like liberal arts students. That means it gives you a very clear understanding of who should read this book. Further, you can see it is written over here, if students do not do a good number of exercises, they will have difficulty following subsequent chapters. That means there are a good number of exercises that you need to solve, and the content is presented here. Here you can see what the author writes. I have used the development of non-Euclidean geometry to revive interest in the study of Euclidean geometry. So it is going from non-Euclidean in order to give a study in Euclidean geometry, which sometimes comes as a very boring topic. I believe that this approach makes a traditional college course in Euclidean geometry more interesting. So it is going to Euclidean geometry from non-Euclidean geometry so that you can have a better understanding and found Euclidean geometry as interesting. So you have found out who are the students, the college going students, liberal arts, general students. There are a lot amount of mathematical exercises given, and it is made in order to make things interesting. So let us quickly, because it's a very fat book, I will just try to give you basically what is the content of the book coming up into the next part of the video. So it will start with Euclid's geometry. As you can see, first 40 pages, it will cover up very brief survey of the beginnings of geometry, the Pythagoreans and Euclid of Alexandria. That means again it is starting with the history, which I found it very important for most of the mathematics students, which they miss. Euclid's geometry, for starting with Euclid's first postulates, attempts to prove the parallel postulate and what are the failures that it was done. And it will have such nice beautiful diagrams also. Next will come the Euclid's geometry, still continuing Descartes' analytic geometry, briefly on the number pi, Then it will come to logic and incidence geometry, which will cover up areas like elementary logic, theorems and proofs. So you can see here that if hypothesis then conclusion, isn't it? So base angles of an isosceles triangle are congruent, then can be translated as if a triangle. So it will give you an understanding of the logical propositions, and from there how you proceed. So it will also cover the logical rule, the statement, even the signs, so beautiful. See that it means the same thing as H and C. I mean to say what it is. So or, not, etc. All those things are beautifully covered in this book. It will also cover up definitions and brief history of what is called real projective geometry, which is also important, projective affine planes and so on. It will cover areas like Hilbert's axioms. So what were the flaws in Euclid which led to axioms of betweenness and congruence axiom 2. Then it would cover up what is called a neutral geometry, which would cover up Zachary and Lambert's quadrilaterals, angles, some of the triangles, history of the parallel postulate by Proclus, Equidistance and Wallis. This is important because until you understand the history of the parallel postulate, how will you understand the next proceedings? So the next would be Farkas Bolyai, that is the father of Janus Bolyai. A very important historical story will be there. You can read through it. Then comes the discovery of non-Euclidean geometry with Hilbert spaces, parallels with Admit and Common, and you will also come to know about Gauss, Riemann, and the next person I'm not mentioning, hope you know, you can put up his name, who is the last person, a very young talented mathematician, into the comment section of this video. Independence of the parallel postulate like the Beltrami, the Poincare's model, and from the hyperbolic plane it is covered. Philosophical implication, most importantly, fruitful application, what is mathematics about, the controversy about the foundation of mathematics, and the fruitfulness of hyperbolic geometry and other branches of mathematics, for example, cosmology, art, etc. So you can now see that even the philosophical implications and what are the fruitful applications of geometry and other areas are being also covered. The geometric transformations are also being covered in details, which would be the Klein's L-angle problem, the half turns, rotations, reflections, and so on. Further results in real hyperbolic geometry, which will be the same, the coordinate and real hyperbolic geometry, followed by the appendix and other Riemannian geometry, including Hilbert's geometry without real numbers. So if you take my honest review, I would say this book is an absolutely great book which will make you understand about non-Euclidean geometry. It helps you how to learn non-Euclidean geometry. Most importantly, I would say you will come to know it was not Einstein, but even prior to him there were concepts like manifolds and etc. And this is perhaps the easiest and the first step that you take into understanding the world of geometry of curvature and surfaces. It would give you a very good historical and mathematical understanding of Euclidean and non-Euclidean geometry. Now, because we are speaking of both the, I would say, the historical and the mathematical approach, the next book that I would speak about is a book which is called On the History of Differential Geometry. I would say this would be again very important. A part of the differential geometry would be covered. It is called The Worlds Out of Nothing. Although it is a book on non-Euclidean differential geometry, but I would say it is a book basically on what is called evolution of non-Euclidean geometry. It is by a very, very famous professor, Professor Jeremy Gray. I have read many books, historical books, even how I would say real analysis, etc. came into history. Very famous professor. I don't know whether you know his name, but he is one of my favorite. So Gray studied actually mathematics at University of Oxford, and then he actually dedicated mostly on the history of mathematics. These are some of the great books as I was talking about: The Real and the Complex Analysis, Simply Riemann, A History of Abstract Algebra, Change and Variation, that is about the calculus, and this is the most important and a very recent book which I have already gone through, Jeremy Gray's Henri Poincare, A Scientific Biography. So all these books are very important, very, very good. It's an excellent read. You come to know a lot, those who are interested about the history of geometry. Now there are some quick facts about this book, Worlds Out of Nothing, which I would like to give. The first thing is that Worlds Out of Nothing is the first book to provide a course of the history of geometry in the 19th century. Now there are 3 chapters which are devoted to writing and assessing work in the history of mathematics, which I am not covering in the video, but I have covered in the earlier videos of differential geometry. That means when you are assessing a historical work, especially in mathematics, how do you question, how do you make the hypothesis? So it is really important. And also the final part of the book concentrates on how projective geometry, as exemplified by Klein's Langen program, rose to importance. It also concludes with the discussion of geometry and formalism, examining Italian contribution and Hilbert's foundations of geometry. So this is a very important fact which makes the book quite apart. I'll just glance over. These are very some of the reviews. I mean, so it's an excellent book, no need to go about the reviews. Now, there are quick facts, again, once more for this book, is that this book actually offers a number of unfamiliar ways in which mathematics can be taught. That means its relations to philosophy and to physics are noted, at times explicitly discussed, and indeed quite deliberately the book discusses some of those aspects in the 19th century geometry of interest to philosophers of mathematics today. That means it gives you an understanding about what is called the philosophy of mathematics, because the book is about mathematics, but it is not a mathematics course. Original motivations matter, individual critical judgments matter. And for me, that means this is not about the course, but it's a book in mathematics. This is very important. Also, this part is important, which I am highlighting now in red. In a much more modest way, the book that invites you to think about how imperfect judgments can most reasonably formed has a certain justification. So imperfect judgments can most reasonably be formed has a certain justification. So how do you actually form a judgment that this is right and this is wrong? That part is also covered in the book. And here you can see himself, Professor Gray gives a recommendation of Marvin J. Greenberg's, whose Euclidean and Non Euclidean geometry I warmly recommend for its many insights from the standpoint of modern geometry. That means it is Professor Jeremy Gray is also citing this book, Euclidean and Non Euclidean Geometry, which I have already covered in lesson number 14, which book to start with, where is a detailed analysis and review of this book is given. We come now to the topics briefly covered in this book. Here are the topics which you can actually pause and look into it. I won't utter each and every. It starts with the mathematics in the French Revolution, theorems in projective geometry, Lambert and Legendre, and then it goes into Gauss. Further, it covers areas like writing. Now this part 137 to 147, sorry, this is something which is related how to write the history of mathematics. It covers about Mobius duality paradox, higher plane curves, complex curves, Riemann's publications, and a lot. Differential geometry of surfaces and other things are covered. Non-Euclidean geometry accepted, then the writing. The fundamental geometry, that is the projective geometry, is also covered. The disk model of Poincaré, the geometry of spaces, and finally the writing assessment questions, and followed by the bibliography and the index. So from my point of view, I would like to quickly let you show what is the content of the book. As you can see, it starts with Monge, right, about the descriptive geometry, and this is how the figures are quite well clear and you can go through this book. Then comes Poncelet, and one of the founders of modern geometry, which covers projective spaces, perspective and visualizations, and every single details. Then come Poincaré's polar and duality treatise on the projective figures, and then you will see theorems in projective geometry and several other details. Euclidean geometry, the parallel postulate and the work of Lambert and Legendre, followed by the non-Euclidean parallel postulate is also covered. Then comes the Prince of Mathematics, Gauss's contribution. Very importantly, Janus Bolyai's new geometry. You see the figures are absolutely clear. The fundamental figure of Bolyai's geometry, Bolyai's F surface, and so on. Then comes Lobachevsky, we call him the founder of non-Euclidean geometry. Then comes Mobius algebraic versions of the geometry, the mathematical theory of planes and curves formed by complex curves. Then comes Riemann, his contribution of Riemannian geometry, and this very important book, the On the Hypothesis which lie at the base of geometry, considered to be a golden contribution in the field of mathematics. Then followed by differential geometry of surfaces, is the geometry of space Euclidean and non-Euclidean. If you take my honest opinion, I would say this book is definitely the best because it covers everything about the history of differential geometry, and it follows a lot of limitations in terms of geometry. What are those limitations? What are the concepts which are developed? A compact and chronologically ordered sequence. The book emphasizes a lot about projective geometry, and the best guide to learn about the mathematical geniuses here, how, where, and when these ideas actually came from. So it is actually in the history of geometry of the 19th century. However, it covers a lot about non-Euclidean geometry. Now, my next recommendation is to build a very good solid foundation again on Euclidean and non-Euclidean geometry. And this is quite I won't say a very renowned book. However, this book, Foundations of Euclidean and Non-Euclidean Geometry by Ellery B. Golas. And actually he completed from Ohio University and wrote few books, but this book this is quite good in terms that it gives you a very good understanding about Euclidean foundations, etc. So if I divide the book, the part 1 is actually to motivate and approach elementary geometry. The second part, Professor Golos writes about to introduce the student to the rigorous approach, and the third part would be which is related to non-Euclidean geometry. Very precise and very point-to-point approach about the book. So you can see that part 1 starts with ingredient and tools, that is finite geometries, axiomatization, and then it goes into the foundations of geometry, congruence and comparison, and so on. Further, as you can see, this is something what sets the book apart, and I would like to show you this example. Now you see he writes that let us define a pencil as a sharp tool used for writing. Now this satisfies the criterion of simplicity, which means that any definition should use ideas and words that are simple or simpler than the idea or words being defined. That means how do you actually make a definition? So to anyone who does not know what a pencil is, the following definition would be incomprehensible. A cylindrical instrument tapering to a conical point as employed by an amanuensis. So this definition actually won't work, but we say that a sharp tool used for writing. So why I am telling you this? Because this is how basically the definitions are wrote in mathematics, and this is how a definition should be written. So once you read this book, you will understand how definitions become simpler. So it is simply not possible to define every word without getting trapped either in an infinite process of defining or in circularity. Dictionary definitions are basically circular. That means from one you go to another and again come back to one. So dictionary definitions are basically circular. So that is why in the suggested definition pencil, if one does not know the meaning of tool, one might look up to find it as an instrument or an utensil. So this is how the important the book is. Further, you see, if you wanted to use a dictionary in foreign language, knew nothing of the foreign language, and had available only a dictionary written totally in that language. So to avoid this problem, it is necessary to choose some words as primitive. That means undefined words, isn't it? And words in terms which all other words of the system may be defined. So the definition of pencil as a sharp tool used for writing satisfies the criterion of simplicity but fails to comply with non-circularity. That means it is not circular, it won't come back. And that is why you see it is written, with this mind let us look into the first three definitions. A point is that which has no part, a line is a length without breadth, a straight line is that which lies evenly with the points on itself. So that means that whenever you are making a definition, it should not be circular, but it would be simple. And these things are taken as primitive. That means it is something which is undefined. You have to assume that. So this is how. So these are not good definition. The first definition do not, then he analyzes about the definitions. Here again you see, if one says he was the greatest mathematician who ever lived, one is not really making a statement, that is, to such a collection of the words. But if the sentence is changed to Beethoven was one of the greatest mathematicians who ever lived, or Gauss was the greatest mathematician ever lived, then the sentence becomes a statement, isn't it? A collection of words to which the labels true or false may be applied. A similar, for example, such sentence as X is a whole number, every dabba is a set of abbas. It is because of this quality of the open statement that such as Russell's can seriously be made. That means you cannot just, if you say that he was one of the greatest mathematicians, etc., it becomes a statement. And if the sentence is changed to this one, the sentence either becomes true or false. So it goes very deep in making you understanding about definitions and how this circularity, etc., should be applied. So now you see that the truth table is also taken into consideration, and it's a wonderful book. So I would say it is one of the best books to build the foundation, easy, clear, and very deep, and makes you a lot of understanding about logic proofs, geometry constructions, and they are very well examined. Now the next and the last book which I would recommend is the book which is named Geometry Illuminated. And this is again an introduction to Euclidean and hyperbolic geometry. So all the books that I'm mentioning you in this video, they are self-contained book, and they are quite well designed so that you really don't have to look for any other book. So this is from the Mathematical Association of America, MAA, and this is Professor Matthew Harvey. And the Geometry Illuminated is also divided into 4 parts. The part 1, neutral geometry; part 2, the Euclidean geometry; part 3 would be Euclidean transformation; and part 4 would be what is called hyperbolic geometry. Let me show you what is the content of that. This is the neutral geometry. So it will start again with the basics like axioms and models, neutral geometry, congruence, triangles, neutral geometry, polygons. So these are actually Euclidean geometry. So circles, circumference. But you see that if you look and go through this book, this one single book will cover up almost everything. Then it will go into transformation, because when you move from Euclidean to non-Euclidean geometry, there are a lot of transformations which are being made. So analytic, isometries, reflections is indeed great. Part 4 will cover up hyperbolic geometry, which would be something like pseudosphere, geodesics on the pseudosphere, and so on. So it is basically building the foundation of Euclidean geometry and then moving into hyperbolic geometry. So this is the content of the book, again to give you just a quick snapshot. So you can pause the video at any point of time, because the writings are too small. You will get an idea of this book. So overall, I can say the book is divided into 45 chapters, 1, 2, 3, 4, and 5, and so on. Hyperbolic geometry is what it concludes. Very easy to read. Got a lot of colored illustration. Euclidean hyperbolic geometry are very much covered in details. And you can see this is actually the contents, axioms, and models. Now this is something which I have, illustrated and made it more, so that you can now see how beautiful the color diagrams are. So here comes the congruence, angle side. That means it's a school level mathematics. So it starts with this, the axioms of continuity, and you see it uses rulers, etc. It's fascinating. You won't actually feel bad if you really purchase this book and go through this. So this is again chapter 9 starts with polygons, and then it goes into orientation of hyperbolic isometries, clear colored pictures and illustrations, which makes things further. So here you can see, but it says that it is not in color. But mind it, when I read through the book, I got a colored version. And this book a pleasure for anyone to read. The book is very well written, and I did not have any background in geometry, but still that person is telling that he has understood the book. Now, in spite of all those things, what remains in our mind is the last question: in which sequence you should read all those books? Because without a sequence, it becomes a problem. It creates confusion. So these are the sequence. First, you should start with a brief history with Professor Jeremy Gray's book. It is an absolute pleasure read, and you can read it when you are at leisure. Second would be build up a strong foundation of Euclidean, non-Euclidean geometry. Extend that to Geometry Illuminated, which will cover up hyperbolic geometry, and then go with Marvin J. Greenberg's Euclidean and non-Euclidean geometries. So this would give you a complete understanding. So that's all for today's video. I would pause now and thank you very much for those who have taken up time to watch this video. If you have liked this channel and this video, please do subscribe and click on the bell icon to get all the notification from Physics for Students. You can also contact me at this email ID, and don't forget to like to my other channel, General Relativity Explained, and please do subscribe there. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be continuing with this series on how to learn General Theory of Relativity. We have covered 5 episodes. Thanks a lot to you for giving so much views, likes and sharing. And Physics for Students will continue surprising more with additional videos on physics and mathematics. We will soon meet you, but till then, goodbye.